again. My name is Kudla. I'm a sophomore at Providence College, and this past summer, or over the past year, I've been doing research on the Baryonic Tully-Fisher relation for galaxies with supernova distances. And before I begin, I would like to thank my research advisor, Dr. Joseph Rubato, right here in the front, as well as the undergraduate Alfalfa team. And of course, I would like to thank the National Space Grant College and Fellowship Program for funding my research and making all this possible. This is just a brief outline of the different points I will be addressing throughout my presentation, but I have bigger slides for that. So for the brief overview, what is the Baryonic Tully-Fisher relation? It's a long few words. So the Baryonic Tully-Fisher relation, or the BTFR for short, it is the relationship between the baryonic mass, or the stellar and gas mass combined, as well as the rotational velocity for a collection of galaxies. And this can be used to estimate galaxy distances within the local universe. So my research aims to eliminate or minimize the velocity scatter present on these graphs to the right. So the first graph you can see here, this is the Tully-Fisher relation, which was established first, and this plots the stellar mass with respect to the rotational velocity. For lower mass, lower rotational velocity galaxies, you can see there's significantly more scatter, and that's how the BTFR was created, where it plots, instead of just the stellar mass, the stellar and gas mass combined with respect to the rotational velocity. And there's significantly less scatter, but there still is scatter. So my research instead, because for gas masses, the way this is derived is through using the galaxy distances. We are using now more reliable distances, which are, instead of being obtained via redshift, the supernovae they host. Here's another BTFR template, and just to reiterate, my goal is to establish a new BTFR, or just a more advanced template with minimal scatter. We will have more accurate points using, instead of just any galaxies that host type 1a and 2 supernovae. For methods, just a brief outline. We began last summer with the proposal submission process to the Green Bank Observatory. And then, while waiting to hear back whether the proposal was accepted or not, we began analyzing our archival data, or data we already had reliable and accessible spectra on. And then in November, we heard our proposal was accepted, which was very exciting. And we began the observation period, which we're in right now. We are still looking back at our archival data and in that analysis period, but the Green Bank observation is more time sensitive, so we're more focused on that right now. And then what comes after this, I will address at the very end. So for the proposal submission process, we began with roughly 700 galaxies hosting type 1a and 2 supernovae, and we obtained these matches from the Democratic Supernova Catalog. We posed various restrictions. So the first one was we eliminated any galaxies with reliable accessible spectra, and these became our archival data sample. Then we eliminated any galaxies that did not meet the requirements of the Green Bank Observatory. So any galaxies that fell outside the declination range, velocity range, redshift range, they were removed from our sample. Third, we eliminated any galaxies of improper morphology or orientation. They just would not contribute as much to our template BTFR as other galaxies would. And then finally, with our remaining sample, we looked at their optical imaging from Sloan, and any with probable confusion were eliminated, just to remove any possibilities of not obtaining accurate data from Green Bank. And then at the beginning of August, we submitted the proposal and heard back in November, and not only was it accepted, but it was A-ranked. For our archival data, so we have 128 galaxies with available and reliable spectra. 1 is from H1 Manga, 80 are from Alfalfa, and 47 are from Springab. And from this archival data, we extract their velocity widths, which can be used to estimate their rotational velocities, their H1 flux, which we can use to determine their H1 mass. And then after this, we'll have to go back to their optical surveys once again on Sloan and other surveys to extract their stellar masses. So you can see here to the right, there's 3 spectra for 3 of our galaxies within our archival sample. And they both, or all 3 of them, they plot the H1 flux with respect to the heliocentric velocity. What we take from this graph, this is after determining the H1 flux from the raw data from the telescope itself. But what we want to do is measure the distance between what we call the double horn, or these two peaks in the graph, to determine the velocity width. And we already have the H1 flux on these graphs. Now for the observation process, which we're in right now. We have more galaxies in this sample. We have roughly 220, and we measure them in 5-minute on-off pairs. And once we have this data on each of these galaxies, they will undergo a data reduction process where we will once again extract the velocity width, the H1 flux, and we will go back to their optical surveys for their stellar observations and stellar mass. Once again, there's 2 sample spectra from this sample, and you can see they look relatively similar, but they're obviously different scales on or different velocity widths on their x-axis and different H1 flux. But down here you can see this graph is not the same as the other 2. This represents the radio frequency interference at Green Bank, which we do have to take into account, which we did not for archival data because this was already having undergone this data reduction process. But we use this to take into account that there are other detections at Green Bank that we need to filter out of our data prior to analyzing it. So what comes after this? Where do we go from here? We will have had all 220 of our observation galaxies and 128 of our archival data, and we can determine the net gas mass from the H1 flux and the galaxy distances. The galaxy distances, once again, to reiterate, were determined from the supernovae they host. Then we can determine their net stellar mass from the optical surveys, their rotational velocities using their velocity widths, and then with this we would plot the net mass, like the gas and stellar combined, with respect to the rotational velocity. And hopefully it will be much more correlated than this BTFR to the right. And just where we stand right now, we are 20 of our 132 observation hours in, and of these, throughout these hours, we've observed 52 of our 220 galaxies, and of these 52 galaxies, 30 rough detections or tentative detections. So here are some important references, and before I close, I'd once again like to thank the NASA Rhode Island Space Grant, the undergraduate Alfalfa team, as well as 2 NSF awards listed, Providence College with Dr. Rovato, and the Green Bank Observatory. Thank you, and I'd be glad to answer any questions.